I'll hop back and forth. Thank you.
Yeah. Yes. Penny, are you ready to present?
Yes.
The recording has started.
Yeah. Uh, so can you see my yeah.
Yes.
Okay.
Yeah, we can see it.
Yeah. Let's start. 1 second. Let's start. So hello everyone, my name is Penny, and today I will present my capstone project titled Predictive Inventory and Procurement Optimization for Cross-Border Furniture Retail. This project is focused on designing a system called Smart SCM for a small furniture retailer. The system combines inventory tracking, customer order management, sales analysis, demand prediction, and replenishment recommendation. And here's my agenda. Let's go through it. First we go to the problem statement. Uh, yeah. For the current business process, most retailers mainly depends on manual spreadsheets and reactive per cash purchasing decision. This creates information delays, especially because cross-border furniture replenishment can take a long time. The main conflict is between the stock out and overstock. If the company does not order enough inventory, it may lose sales and reduce customer satisfaction. However, if it orders too much, it increases warehouse costs and ties up business capital. Therefore, the project proposed a decision support system that combines inventory visibility, sales forecasting, and explainable replenishment logic. And for the motivation, furniture inventory creates a particularly high-risk environment because furniture products are bulky, expensive, and costly to store. In addition, long production and international shipping lead times can make it difficult to respond quickly when demand changes. These delays can amplify the bullwhip effect, where a relative small change in customer demand creates much larger change in upstream purchasing and inventory. Motivations for this project is to reduce reactive procurement and provide store manager with more organized information and database recommendation. For the background of this project, the project is based on three important concepts. The first is the cross-border furniture logistics. A product may move from a factory in Foshan through trans-Pacific shipping and finally to a warehouse or showroom in Seattle area. Each stage creates additional lead time and uncertainty. The second concept is the bullwhip effect. Delay or inaccurate information can cause unnecessary inventory fluctuation throughout the supply chain. And the third concept is the technician foundation. Machine learning can support demand prediction, while multi-stage inventory tracking can improve visibility across production, transit, warehouse, showroom, and reserve inventory. For the system matrix, it compares four research source with the smart SCM approach. The first is a fuzzy body focus on machine learning demand for forecasting and its relationship with supply chain performance. And the second is the law. It connects forecast accuracy with bullwhip effect reduction. And the third one is the DOL and its colleagues focus on automation and coordination in cross-border inventory management. Hui and its college exam multi-economy inventory optimization cross multiply distribution stage. Smart SCN combines these ideas in particle prototype for a small cross-border furniture retailer. It uses reinforced prediction together with its plannable inventory and replenishment rules. And here is this literature shows three common themes. The first is better forecasting can reduce reactive procurement and improve supply chain decisions. The second is cross-border operation require inventory visibility across multi-stages rather than only tracking a single inventory total. Third is that prediction becomes more useful when it is connected with optional data, such as current inventory, incoming stock, and lead time. This observation provides academic foundation for my project. And here's the bibliography we go through quickly. And let's move to the approach. My project use a five-step approach. The first is that I develop a full-stack application using React and Fast API. And then I create a structured data layer using secure chemical and a relational database. Third, I imported stimulative furniture sales data for analyze and model development. Then I train a random forest regression model to estimate sales demand. And finally, I combine predicted data with inventory information, lead time, incoming stock, reserve quantity, and safety stock to generate explainable replenishment recommendation. This hybrid method support managerial decision without completely replacing human judgment. And for my core system modules, I this includes 5 major business modules. The dashboard summarizes important information, including orders, profit, and inventory warming. The product management stores product details such as SKU, category, material, color, cost, and selling price. The multi-status inventory management checks products across production, transit, warehouse, showroom, and reserve stage. Customer order management records order progressive from inquiry to delivery. Finally, the replenishment support analyze demand and inventory information to generate reorder recommendation. And here is my solution architecture. This diagram shows the overall system architecture. Store staff and business manager interact with the reactive frontend. The frontend contains page from dashboard, inventory, order, cost, and profit, and replenishment. The frontend communicates with the Fast API backend through REST APIs. The backend handles products, inventory, order, business logic, and stores structured data in the secure database. The Python analytic prototype reads sales and inventory data, perform random forest prediction and inventory risk analysis, and generate replenishment results. The dash connection indicates that full integration of analyzed prototype into the web application remains further work. And here's the UI design. It designed for the store employees who may not have technical background. The dashboard present the inventory summary, pending orders, low availability, products, profit information, and replenishment suggestion. Then is the product page. Yeah, it shows the information of each product and also, oh no. And the customer order page shows the details of the orders, and then the smart replenishment shows shows which product should be is recommended to replenish. Yeah, and then it comes to the implementation. The implementation includes 3 major areas. For the front end, I develop a React page for the dashboard, inventory, cost, profit, and replenishment. For the backend and dashboard, I created fast API endpoints, secure argument models, and alphabet database migration. For data and analyze, I implemented the automated CSV imported random forest demand prediction, inventory risk analysis, and replenishment calculation in Python. The core web application and database function are implemented. And then let's go to the data collection. The project using a cumulative furniture sales dataset from Cargo. The dataset contains 2,500 sales recorded and 14 variables. It has no missing values or duplicated rules. The variables include production information, financial information, and some product information such as material color. This data set is used for explore, analyze, random forest training, inventory risk evaluation, and replenishment testing. However, because it is stimulated data, it does not fully represent the actual store's historical operation, and I plan to use real data in further work. And then goes to the data analyze. The category analyze shows an important differences between sales volume and financial contribution. Cheer has the highest total unit sales, while Sofa produced the highest total revenue and estimate profit. This means that the product with the highest demand is not necessarily the product with the highest business value. High volume categories require frequent stock availability, while the high value category require careful inventory and capital planning. Therefore, procurement decisions should consider both unit demand and financial contribution. And then is the data analyzed by material. This material analysis shows that wood is the strongest material group in terms of revenue and estimated profit. Premium materials, especially wood and leather, generally create more financial value because their selling prices are higher. In contrast, glass and plastic shows weaker overall performance. This result shows that materials should be considered when setting replenish priority. Then is the data analyzed by season. The season analysis shows that fall has the highest overall sales and revenue. And for the business meaning is that seasonal demand piece suggested that inventory should prepare before high demand periods. So replenishment planning should consider both when demand occurs. And then let's go to the model. Yeah, a random forest regression model was trained to predict sales volume. The category input features includes category material, color, and season. The numerical features include the price, cost, profit, and so on. And category variables are converted using one-hot encoding because they are passed into the before they are passed into the model. The random forest contains 300 decision trees, and the data is divided into 18% for training and 20% for testing. Revenue was not used as an input because it directly related to sales and could not create data leakage. And then is the model performance. The model was evaluated using MAE, MSE, and R square. The overall performance is pretty good, which means that which overall the model performs well on the data set, but results must still be interpreted carefully because the data set contains intentionally designed and demand patterns. And then let's go to the model limitation. Although the model produce strong evaluation results, it still has several limitations. First, the dataset is stimulated rather than collected from actual store operation. Second, it does not contain a true sales history. Important demand drivers such as promotions, holiday, customer traffic, production age are not available. Some financial variables require further review to ensure that did not indirectly reveal the target variables. Finally, the current evaluation use one trend test split. Cross-validation and real history data will be provided for a more reliable evaluation. Then let's go to the replenishment recommendation. This algorithm convert predicted sales into an operational purchasing recommendation. It first used the predicted sales to estimate demand during the replenishment lead time. Next, it calculates safety stock and the reorder point. The algorithm then compares the reorder point with available inventory, reserve quantity, and incoming inventory. If the expected demand is greater than the available supply, the algorithm calculates the reorder gap and suggest a order quantity. It also generates a priority score so that the manager can identify which products require most urgent attention. And then let's go to my finding. The project produced several important findings. First, procurement decisions should combine sales demand with financial value. Second, inventory risk should be evaluated by comparing inventory with demand rather than looking only at inventory quantity. Third, the machine learning pipeline can support demand estimation, but real historical data is still required before production use. Four, a hybrid method is more suitable than a pure black box model. Machine learning estimate demand while explainable rules calculate safety stock, reorder points, and suggested quantities. Finally, category level and material level information should be included in inventory and replenishment decision. And here's my conclusion. This capsule designs smart SCM as a predictive inventory and procurement decision support system for a small cross-border furniture retailer. The project addresses long replenishment cycle, bulky products, warehouse pressure, fragment manual tracking, and reactive purchasing. The prototype combines product management, multi-stage inventory tracking, customer order management, course and profit analysis, sales prediction, and explainable replenishment logic. The project demonstrates that machine learning is most useful when its output is connection with real operational rules and business information. And for my further work is that my further work is to integrate the replenishment algorithm into the fast API backend as a reusable recommendation service. And then is to connect the React replenishment page to the backend and display recommendation results directly into a dashboard. The most important work is to replace the stimulated data set with real historical sales, inventory, and lead time data from the first for the furniture store. After the real data is collected, the model can be retrained, validated, and compared with additional forecasting method. Let's go to my demo. Yes,
Hi, Penny. Sorry to interrupt, but you
sorry.
have 3 minutes to complete your demo and Q&A.
Okay, okay. I will go through it quickly. So let's go to my backend first. Oh, sorry. Yeah. In this this is the backend page that store the data and the front-end page can read data from it. It has the product inventory orders and replenishment page. And here is the front-end page. This is the main dashboard of the system. It provides a quick overall of inventory, active customer orders, revenue, profit, and possible replenishment alerts. The purpose of this page is to help the store management understand the current business situation. And here is the products. It has the SKU, the product name, the category, and materials, all the information. Also, I can use the search page to, and also the category to select select products, and then goes to the inventory page. The inventory page is one of the core parts of the system. Instead of storing inventory and as only one total quantity, the a smart SCN tracks each item by its operational status. So you can see the like this products. You can move the status of the products from in production to in transit, and yeah. And also you can see the past status of the of each product. And then let's go to the order page. The order page is to track the customer's order life cycle. It includes inquire, deposit pay, preparing, schedule delivery, and delivered. The system also can support canceled and refund status. Yes, you can see that there. You can use the app. You can view the details of each product and update the status of each product from inventory to preparing, schedule delivery or delivered. Yeah. And after the new status is created, they will be automatically changed to other. Yeah. And here is the replenishment. In this page, it connects the machine learning model with operational inventory data. The first step is the demand model training. Yeah. And after the training, now I already training because it takes quite a long time to train. The system stores the active model and displays the training row counts. In the current model, yeah, it shows the here. The manager can configure the demand period, supply lead time, safety, stock period, and minimum order quantity. The manager can also decide which inventory in production or in transit to be counted as incoming.
Hi, Penny.
Yeah.
I'm really sorry to interrupt your presentation,
Yeah.
but we are like 1 minute overdue with your demo,
Yeah.
and we still have to go through the Q&A.
Yeah. Okay. Yeah. So basically, I'm over because this is the last page. I will want to show. Yeah. So now, do you guys have any problem?
Yeah, she said we are a minute over, Penny. I think we should stop. Thank you.
Yeah.
Let's go to the questions, please. Morgan?
Does anyone have any questions?
Yeah, it looks like Morgan is swapping to other
Yeah.
sessions. So, Namrata, do you have a question? Or Seth, do you have a question?
No, I don't have any question.
No, I don't. I think I've seen Penny's work throughout the quarter. It's a great presentation. Yeah.
I have a question, if I may.
Yeah.
So, Penny, you've used random forest, right?
Yeah.
Do you have used any other machine learning technique? Because at the end of the day, there's also a time element involved. So there's got to be some sort of a time series that will be required. What have you done with respect to that?
Yes, I have used logistic, but it does not explain the data very well. So I compare several algorithm, and I choose random forest because it has the highest result. Yes.
So sorry, I'm still unclear. Random forest can be used for multiple purposes. Is this classification? Random forest classification?
Yes.
Okay. But then random forest classification does not help you with time series. It doesn't capture seasonality. It doesn't capture cyclicality. And there is a demand forecast, which ends up causing inventory issues. Have you considered that as a potential reason why some of the other models did not work for a good reason?
Actually, no. It is, yeah. I didn't consider that. Yeah.
Yeah, you have to use random forest as some sort of a temporal model. All right, thank you. I think you got my answer. You got my question answered. Thank you.
Thank you.
Back to you as the moderator.